Hello, and welcome to part 6 of this series of videos that introduce the mathematics of signals. For a full playlist with all the parts of this series, please click the link at the top of the screen. In this part, we will look at complex time harmonic signals. So a quick outline. We're going to try and answer questions such as: how are complex numbers used to describe real signals? What benefits does this bring? And what changes are required?
Okay, so it makes sense to start this video by asking what are we hoping to achieve? Let's be fair, complex numbers sound complicated. How are we hoping that using them might benefit us? So the short answer is we're looking for an easier way to represent phase changes. So as I mentioned a couple of times when we were talking about Fourier series, having phi stuck inside cos in cos omega t plus phi makes it difficult to handle. So we had this kind of form where you had these separate a and b terms, and that was okay, but a and b don't really relate to the magnitude and phase quantities we want to think about when we're actually dealing with signals. So they work, but they're not super useful. So we're kind of looking for a better way of doing things. And here's a quick sneak preview, because I think it's easiest just to tell you the answer. We will see that complex numbers turn phase change into multiplication, and that makes a whole world of things a whole load easier, as we will find out. And we already know that this is possible for 180-degree phase changes, so it's not so unreasonable to think that phase change could turn into multiplication. If you think of the phase reversal button on consoles, this achieves this by negating the signal, i.e. multiplying it by -1. And that exploits the fact that for cos omega t or sin omega t, if you add or subtract pi, what you get is the negated version of the signal. You get minus sine or minus cos appropriately. So that works, and that works for any frequency. So the question really is, what would we need to multiply a signal by to achieve a different phase change, so plus or minus 90 degrees. Maybe that's where we'll start. So we can do 180, let's see if we can do 90. And to really understand what we're going to do here, we've got to go back to these kind of pictures where we kind of represent time harmonic signals as these kind of rotating cyclic kind of behaviours. So just to recap, I've got the signal that we're thinking of, a cos omega t in the vertical axis here, and then in my left hand graph I've got a sine omega t, so going in the horizontal axis, and then in the graph on the right I've got time. So if I just press play, we can see that the angle in the left hand graph is omega t, so it's going to change with time. Phase is going to increase with time. Off we go, and that's going to scribe out a nice cosine graph as that thing goes round and round. We're just sort of projecting it, the two dots are going up and down together. So we're just plotting the time history of what that thing did on the left. But importantly here, the vertical axis is the quantity xt that we're observing. So that's why it was in the graph on the right. But what this circle shows you is that there's something else going on. And as I talked about in my last lecture about energy, I would argue that the best way of describing this is that it's the other quantity that we're not seeing, we're not observing, and it's the one that contains a complementary energy. So oscillators have this property of having kind of constant energy, and it's being exchanged constantly as the phase changes between the quantity that we're observing and something else. And this is the something else, whatever that might be. And I speculated in my last lecture, if you care to go back to it, as to what those sort of things might be for different systems. And that works. Here we go for just the one, but if we actually stuck a phase change in there, we can show something else, a different signal, yt with a slightly different phase. It's actually got a phase lag, phi equals minus pi over 3 in the example I've chosen here, so phi actually goes backwards, which is clockwise. And what we'll see is this thing rotating anti-clockwise, and the blue dot representing y will follow with a phase lag of 60 degrees. So let's just run that. Off it goes, and you can see that indeed the blue line is trailing behind the black line, so it's got a phase lag. And these types of plots show how phase is an angle. They're extremely useful, but you need to be able to get the 90-degree version of a signal from itself in order to get them. So what we're kind of seeing here is that you can express any arbitrary phase quite nicely so long as you have the 90-degree version. But just sticking with the original question, is there a way we can write the 90-degree phase change as a multiplication, like we can for 180 degrees? In this neat example with cosine waves, I just knew what the 90-degree phase version was. It's a sine wave, so that's easy. But if you had something else, what would it be? Well, it's a bit more difficult. So let's see if there's a better way of writing this. So I'm just going to simplify this graph for a minute. So I've got x at the left-hand vertical axis still. I've still got the same axis at the bottom. I'm just pointing out here that my theta in this graph represents omega t plus phi. So it's going to represent the quantity omega t that's increasing with time. So that's the one that makes it go round and round. And then phi, whatever it is the offset starting phase at time equals 0. And I've just written them both as theta here just because I haven't got space to write all those letters. So the first thing I'm going to do is just to change convention a little bit. So I'm just going to rotate this graph around because the convention is that we're going to put cos on the horizontal axis. So I'm going to have to stick with that now. So let's just tidy that up. And also, just to link back to this energy idea, I'm just going to give a name to the signal on the vertical axis there, and I've called it x perpendicular. That's what that little funny symbol's supposed to mean. I've kind of made this notation up, if I'm completely honest, but it does have some specific mathematical meaning. It's the bit that's 90 degrees out of phase, and it has a mathematical fancy name. It's called the harmonic conjugate, and for arbitrary signals they're related through something called the Hilbert transform. But as I said before, for these kind of time harmonic signals it's easy to understand. It's just a sine instead of a cos. So it's 90 degrees different. And as I said before, with both things it's easier to see the complete picture because there's nothing missing. You're not only seeing x, you're seeing the other thing that is going on. So is there a way of writing this more succinctly? So we're going to go back to the fact that this is a little triangle here, and we're going to note that xt was the horizontal, so the size of the triangle, just thinking about the length of the line out to that black dot that represents the point where we are on a signal. And then the vertical axis is this complementary signal, and the amplitude of this line here is A, as we've seen before some of the other animations. And just to reinforce the point from my last lecture, the point here is that the amplitude squared of both these signals, the one we're observing and the complementary one we don't see, is constant. It's A squared. So basically energy is going to be constant. So that's an important aspect of all of this. As I said last time, is why we get circles and why we get trigonometric functions. So let's find a different way of writing that. We want to represent phase change by multiplication. So how are we going to do this? Well, let's start off with some simple cases. So if you want to do a full rotation, 360 degrees, you get back to where you started. So that's like multiplying by 1. Times something by 1, you get the same thing. Go around 360 degrees, you get the same thing. So yeah, okay. Half rotation, I've already said. You want to do 180 degrees. That's like the phase shift button on a console. That's -1. It's just flip the polarity. So that's also easy to understand. But what I want to know is how to do 90 degrees. What is question mark? What should I multiply this by to get a 90 degree phase shift? Well, the first two give us a clue, because rotating by 180 degrees twice is a full 360 degree rotation. So multiplicatively, we say that 180 degrees plus 180 degrees is 360, and -1 times -1 is -1 squared, which is 1. So multiplicatively it works. You know, if you do half rotation twice, you get back to where you started. So yeah, okay, that makes a lot of sense. So we can kind of reframe this by saying that what we're looking for, this question mark, whatever it might be, is something that when you square it, it gives you -1. And that is where imaginary numbers come in, because someone else, and I don't know why they were thinking about it, thought of this, and they thought, what happens when you take -1 and you define something that you have to square to get that? So well, you find this imaginary number, I, that when you square it, it is -1. And really, that's the answer. Great. It can represent a quarter rotation. You know, if you square it and it gives you 180, then that means it represents 90. And to be perfectly honest with you, I do think that calling this an imaginary number makes it just seem a whole load more harder than it really needs to be, because all it's really telling you is that you shift to some, I would call it an orthogonal quantity. You're shifted 90 degrees. You're shifting to this other energy that we can't see. You know, it's just a different behaviour of the system. And calling these imaginary numbers, or even worse, complex numbers, just makes the whole thing seem really hard. And as I'm trying to show graphically, it kind of isn't that hard. You just got to get it in your head that I is 90 degrees. But where we really win is that all that mathematical machinery is there ready and waiting. We can just pick it up and run with it. So if we take the standard form of complex numbers, then we can see that we've got a real part A, which is the real part of Z. It's got an imaginary part. And if we just say that these are the axes on our diagram, then this is something called an Argand diagram. And Z would be the coordinate of the dot on the circle end of the little line, which is the point on the wave that we're thinking about. But actually, it's best understood as a vector, as a kind of a vector sort of pointing out from the origin, taking you to there. So it's a coordinate, but it's also a vector from the origin. And you can see that its length projected down to the horizontal axis is going to be A, which is the real part of Z, and the vertical part is B, which is the imaginary part of Z. I should say at this point that if all this just sounds like complete mumbo jumbo and you've not come across complex numbers before, then actually you should probably stop the video now and go and look at a little primer, because I'm not going to try and explain them all from scratch, or I'm just going to kind of talk about them like you're reasonably comfortable with the general idea. As I say, it makes it seem harder than it is, and there's a certain suspension of disbelief here, really. You've just got to accept that I squared's -1 and roll with it, and follow the maths and see what comes out. And as I'm saying here, it turns out the maths is useful, so great. But really, what's kind of important here, and I think this is the most important point, is that complex numbers have 2 dimensions. So they're not just a scale in one direction like a normal real number is. We've just got positive and negative. We've got a whole plane of numbers, because we can go positive and negative in real, and we can go positive and negative in imaginary. So we can actually go anywhere across the whole plane. So they're like so when I say they're like a vector, that's what I mean. Is they've actually got 2 numbers hidden inside them. And one of them is the real quantity we're observing, so that might be xt, might be related to this point on the real axis. And then the other imaginary dimension is going to represent this other quantity we aren't observing that holds the energy that this one doesn't. So that's really useful. It's got both these things in one, so you've kind of got 2 waves for the price of one here, and moreover, we're going to see that the mathematics of complex numbers lets you just relate those in a really convenient way. So the first thing here is to say that there's also something called polar form of complex numbers, which is basically related to triangles, right-hand triangles again. And so R is the just distance along that line. You can see hopefully that cos theta would take you down to the real part, sine theta would take you to the imaginary part of Z, so that first equation kind of follows. The length across that line we will call R, which is called the magnitude of Z. So that's this thing in these 2 little vertical lines means magnitude, and it's the real part squared A plus the imaginary part squared B. And this relates directly back to what I was saying before about you square the signal and the complementary signal, you get constant energy. Here we will get amplitude. Yeah, that's what R is going to equal to. And that is all already really useful, but the real thing that actually just sort of really sells it and really makes this transformative is something called exponential form. And again, this is another slight suspension of disbelief here, because there's just some weird combination of mathematical symbols here that's just, why on earth should this go together? But it turns out that it does. E, the base of the real logarithm, to the power of I times theta is cos theta plus I times sine theta. Wow, okay. I can remember being an undergraduate when a tutor dropped that bombshell, and it was just like, oh, what have you done? You've taken two complicated things that I kind of understood separately, and you've just bunged them together into one statement, and what on earth are you talking about? And he completely failed to explain it, and I just had to go away and accept it. I'm going to try and explain it on the next slide, and we'll see if that helps. But just to give you a quick preview, what we're going to try and do here is we're going to say that x is going to be equivalent to the real part of z, so z is like x but with an imaginary part bolted on, and we'll see that we can write that in some sort of exponential form. We've got some radius and this e to the I theta business, and actually if you remember that theta was omega t plus phi, then we can pop that in, and we can remember over here that r is a, and this is more like the form that you're going to see when we kind of go forwards with these things. But if you take the real part of that, see that e to the a omega t phi, real part of that is cos omega t plus phi. So actually what you get out is the signals that we've been dealing with. So this kind of looks a bit inconvenient. We'll see in a minute that actually it's not, that it's actually really, really helpful. But these two things are equivalent insofar as you've just sort of added an imaginary bit on for fun. So, right, e to the I theta plus cos theta plus I sine theta, you what? I mean, this is certainly what I felt when I first saw this. This equation is called Euler's equation. It's named after Leonhard Euler. Now, confusingly, lots of equations are named after him because he was a very, very smart guy. And there's a few proofs following around as to why this is true, or why someone might have ever thought to even consider putting these symbols together like this. What might happen? And I think the easiest way to understand it is by using something called a Maclaurin series. And again, if you don't know what a Maclaurin series is, just stop the video and look it up on Google or Wikipedia or something or other. Essentially what it tells you, if you've got a function of some variable, I've written theta, then it's the value at 0 plus 1 over 1 factorial times the first derivative of the function evaluated at 0 times the variable theta, plus 1 over 2 factorial times the second derivative of the function with respect to theta evaluated at 0 times theta squared, plus 1 over 3 factorial third derivative at 0 theta cubed, etc, etc, etc. So we just kind of keep adding on these extra derivatives, and we get the kind of polynomial in theta turn up. Now, if you do this with cos, what you will find happens is that, of course, cos 0 is 1. First derivative of cos is minus sine. Sine at 0 is 0, so we skip the first order term. Second derivative of cos is minus cos, so we get minus 1. So we get 1 over 2 factorial, which is 1 times cos squared. Third derivative is sine theta again, skip that one. Fourth derivative, we're back around to cos. So you get 1 over 4 factorial, which is 1 over 4 times 3 times 2 is 24, times theta to the 4, and then we're going to skip the odd order 1 at the 5 again, blah, blah, blah. So that's what that looks like. If you do the same thing to sine theta, you find that, first of all, you get 0 for f0, because sine theta for theta equals 0 is 0. First derivative is cos, so that's going to give you something. You're going to get 1 over 1 factorial times cos of 0, which is 1 times theta, so we just get theta. Second derivative, we're back to minus sine. That's going to come out at 0, that's going to skip that. Third derivative, 1 over 3 factorial is 1 over 6 times the third derivative, which is minus cos, so we get a minus 1, theta cubed, etc, etc. That's how kind of these things work out. Now, if you do it to e to the I theta, there's an expansion for this, and e, if you recall, was kind of introduced as the base of the natural logarithm. It has this fantastic property that when you differentiate things, it kind of turns them into multiplication. So whatever you've got in the exponent just comes down as a multiplier. So differentiate it once. Well, so evaluate it at 1, you get, for theta equals 0, you get 1, same as with any exponential. Evaluate its derivative once, you just get the I theta times it at 0, which is 1. Do it again, you get I squared theta squared. times it evaluated at 0, which is 1, and you get the half, and this kind of progresses. So you're just effectively getting the factorials times by some particular power series of I times theta. And if you just collect some of those terms and you realise that the I squareds go to -1 and you can get rid of some of these, simplify things a little bit, you'll get something that looks like that. And if I just put that up there and we just compare these terms, you will see that that is exactly the same. And you add those two together, multiply sine by I, and by some mysterious process you get Euler's formula. So this all just hangs together mathematically. If you just do the derivatives, you just find that this is true, weird as it is. So there we go. So I hope that helped. Maybe it didn't. If it didn't, ignore it. What I'm going to do now is I'm going to talk about multiplication of complex numbers. I said we're going to use multiplication of complex numbers to represent phase, so I better look at how multiplication of complex numbers works. So I'm going to take two complex numbers, Z1 and Z2. To do this in standard form, I expand them into real and imaginary parts, A1, B1, A2, B2, and then I multiply all those brackets out. I get an A1, A2, that's straightforward. B1, B2, that came from IB1 times IB2, I squared's -1, so that becomes real but negated. And then the other two parts just collect together and give you the imaginary part of the whole thing. Okay, it's just like multiplying brackets. Polar form with complex exponentials. Okay, well, what's good is that the usual rules of exponentials still apply. So I've got something to the g and something to the h and the same base, where g and h are just some numbers, integers or real numbers or whatever. Then I just get e to the g plus h, and that actually still works with complex exponents as well. So if I'm going to multiply these two things, I'm just going to get z1 is the magnitude of z1 times this e to the I phi 1, where that was the phase of z1, which I actually haven't written on here, I apologise, in the next line. And then magnitude of z2 times e to the I of theta 2, where theta 2 is the phase of z2. And if I just collect those terms, you can just exploit this exponential rule and combine these I theta terms, and they just add. So we see that the two magnitudes multiply, just change the order, and the phases add. So magnitudes multiply. We get the magnitude of the z1 times z2. It is just the product of the two magnitudes. Easy peasy. If you look at on a scale, an Argand diagram, it's going to appear as scaling. And phases add. If you look at the angle of Z1, Z2, that's what this little funny triangle sort of on its side less than sign means. It means angle or phase of the two together. It's the phase is separately added. It's just the phase of Z1 plus the phase of Z2. Phases add. This appears as rotation on the Argand diagram. So let's look at this with an example. So I've got two complex numbers. I've given some values. Z1 on the left is 3 plus 4i, represented by this triangle. I'm using the same kind of scheme as on my other Argand diagrams before, where horizontal is real and vertical is imaginary. And I've got a second complex number, Z2 is 1 plus 1i. If I multiply these in standard form, Z1 times Z2, yeah, blah blah, just do what I did before, collect some different terms, just multiply those through, so and I will get -1 plus zi if I just follow all that through. So that's a kind of triangle there. It's facing a bit the other way because it was -1. So I've got 1 at the bottom, 7 high. Okay, well, yeah, that worked. That wasn't difficult. Difficult to see how those three triangles are related, to be honest. It's just something that's kind of happened. But we'll see that if we do polar form with complex exponentials, you can actually come up with a reason as to why this has happened. So let's write this out. And the numbers here look a bit weird. Now I've got a 5 for the length of the hypotenuse in the first one because I've picked one of the classic Pythagorean triangle examples. I've got √2 for the hypotenuse of the second one. I put the phases on there. They're pi over 3 for the first one, 60 degrees, and pi over 4, 45 degrees for the green triangle. And this doesn't look really any better, to be honest. But what you have to remember is that amplitudes and phases, which map to the hypotenuse and the angle of the triangle, are the things that you already know about the signal. So this data might look less convenient, but these numbers here are the ones you would already have for a signal. The other ones, the real and imaginary parts, you wouldn't probably have. So this is actually more useful data. And we'll see also it's actually got a better interpretation. Because if we take this, if we kind of think of this second triangle, the second factor multiplying operating on the first one, we'll see that there you put the first triangle and there's Z1. And angles add. So that second triangle sits rather neatly in there and graphically just sort of fills the gap and shows how you get from Z1, the hypotenuse of the blue triangle with the arrow, to Z1 times Z2, the hypotenuse of the yellow triangle with the arrow. It tells you how you get the angles one from another. And you can add those up, and if you do it, you'll find that's 7 pi over 12. Doesn't really matter, but the point is that they sum rather nicely. If you're thinking of this second triangle operating on the first one, then what you can see is it's caused a 45 degree rotation. So e to the I pi over 4 is giving you a 45 degree rotation to sort of rotate that that first vector z1 round into the product of the two. Second, look at the scaling out the front, where the magnitudes have been multiplied, and that you can see that again thinking of the green triangle operating on the blue one, by just sort of mapping that arc length round. So if you did the transform e to the I pi over 4 just on z1 and that's all you did, it would just come round to that point where that arc intercepts the black line on the left. But actually we've also made it a bit longer because we had 1.41 going in there, and that has extended that line by a factor of 1.141. So you can separate these two behaviours into two separate effects. That the phase part rotates and the magnitude part scales. So this is actually really useful graphically. You can just think of this graphically and you can understand exactly what is happening to the signal just pictorially by looking at these numbers. And that's the result. Again, doesn't really matter, but that's the result you would get. So here's the key points. Magnitudes multiply. So the magnitude of two complex numbers multiplied together is the multiplication of their individual magnitudes. And this appears as scaling on the Argand diagram, and as we were seeing before, it's kind of stretching these lines out. And then phases add. So if you look at the phase of Z1 times Z2, it is the phase of Z1 plus the phase of Z2. And this is going to appear as a rotation on an Argand diagram if you think of the second number Z2 acting upon Z1. And also you can see here that actually we were looking for something that would rotate by 90 degrees, but we've done a lot better than that. We can rotate by any angle, any phase, not just 90 degrees. We're winning. So final piece, let's just think what happens with complex exponentials versus time. So I'll just do some real ones first for argument's sake. If you do e to the plus t, it's going to grow exponentially as time increases. There's a little graph there. If you were to take e to the minus t, it would shrink exponentially as time increases. That's the kind of things you get. But e to the I omega t is going to do something different. It's going to do something more like the causes and sines we saw before, because it's built out of causes and sines. It's going to rotate as time t increases at a speed dictated by omega. So off we go. We've got a diagram a little bit like before, though now my real part is in the horizontal axis. I've kind of rotated things around, and I'm now plotting the time history of the imaginary part as well. It's got e to the I theta, that's effectively the coordinate of the dot on the end of the line, and we're going to just let that roll and time increase, and off it goes. And you'll see that now we're sketching out two graphs as we go round and round. We're sketching out a cos graph in the real quantity we're observing and a sine graph in the other complementary part of the energy that we're not observing. That's kind of what you expect, because that's what I've been saying all along. I've just had to graph for the sine part. But what gets really interesting is if you say, well, hang on a minute, let signals have complex amplitudes. So xt is a cos theta omega t plus phi. That's what I've been doing all the way through since the part 4. So let's just bung an imaginary part on there. We'll just say we'll add a convenient imaginary part, I sine theta of the same thing. We'll have them both multiplied by a, and then we'll take the real part, and that will give us xt. So we just sort of added a bit on. It's just made it more complicated, really. But using this Eulers formula, we can then draw this down into this rather convenient, more compact notation, like that, where that just goes to the exponent. And then we can say that, well, hang on a minute, maybe we'd like to split these up. Maybe we'd like to take the I phi, the phase, away from the I omega t, and you will get that. And then we'll say, well, hang on a minute, let's bung the A and the I phi together into a single number c. There we go. And suddenly you get this lovely, really, really compact notation where all these other things just turn into a complex number times e to the I omega t. And in fact, actually, and c captures the amplitude and the starting phase at t equals 0. So it's got the amplitude a and the starting phase e to the I phi at t equals 0. They're both in there. Remember, complex numbers represent two pieces of information, and it's amplitude and starting phase. And these are so spectacularly useful that you'll often see that we don't bother to write the real or the e to the I omega t at all. We just talk about complex amplitudes quite a lot in acoustics. You'll see that if you come on one of our courses. We just throw these complex amplitudes around willy-nilly without any real concern for the rest of it. But this is what they mean. So let's see what effect that has. Now I've got e to the I omega t as before, but now I've got c e to the I omega t. And I've just expanded that out into the a cos omega t plus phi and the ia sine omega t plus phi, just for the benefit of anyone who's struggling to keep up, and also just to show what a big dog's breakfast that bit on the right is. This c to the I omega t is so much more compact and easy to write. And c is a times I phi. In this case, I've chosen a is 1.2, so it's going to make c operate at a slightly larger radius. It's got a bigger amplitude, and I've started with a phase of pi over 4, so it's a bit ahead. Let's let that run. Oh, no, just going to point out that the c acts upon this, so it tells us, like the rotation of the triangles, it's acting upon the black line to give us the blue line. So it's rotated forwards by pi over 4, and it's stretched it out by a factor of 1.2 by the amplitude a. And electrical engineers use this a lot. They call it phasors. You don't tend to hear that language in acoustics very often, but that is what this is. And we'll just see these two things rotate beautifully in phase locked as we did before, but now we've got a complex interpretation. So off they go now. And you can see that not only are they sort of bouncing a little bit out of phase with one another in a sort of pleasing kind of way, but of course we've got the different amplitudes. So let's just watch that one more time. Round and round they go. And if you looked at those two dots dancing on the graph, on either of the real or the imaginary graphs, you'd probably struggle to really totally see how they're related. They just sort of feel like they're bouncing around quite independently. But you see this graph on the left of the Argand diagram, and you can totally see the full picture, that they're just locked together by this fixed angle phi. So quite a lot going on there. Time for a summary. So if you multiply something by a, where a is real, you scale a signal in amplitude. If you multiply a signal by e to the I phi, where phi is real, it rotates the signal in phase. You get phase lag or fade leads, dependent on whether you're behind or ahead in time. And you don't get any scaling because e to the I theta, the magnitude of, is cos squared plus sine squared. Remember, a magnitude of a complex number is real part squared plus imaginary part squared. And those two have the identity of equally 1 because they describe out a circle. So yeah, so no scaling, just rotation from that term there. E to the I omega t does a rotation, but it's a rotation that increases with time, so it's basically a rotation, it's just a spin round, and omega is going to set the speed of rotation in radians per second. And c is this complex amplitude, scales a signal in amplitude and rotates it in phase, its starting phase at t equals 0. And you can break it down into a scaling and a rotation as c equals a to the I e to the I phi. And just to hammer home the point even more, making waves complex makes some things easier. So what you'll see is that we don't bother writing real around everything. We just need to kind of remember that whenever we work with complex quantities, complex signals, this operation will always happen at the end to make something that's actually what you'd measure in the real world. And this is fine because the maths all still works correctly even if you leave things complex. So the mathematicians have done a sterling job of considering complex numbers to the absolute nth degree, and everything that worked for real numbers works for complex numbers. So you can just forget the fact that you need to take it real and just leave it out. So let's think about a complex signal. So xt is c to the e omega t. So as before, but with no real. So our amplitude and phase are both encapsulated in c. I've been emphasising that benefit. But if we look at some things like temporal differentiation, which normally you'd think of as being quite complicated to do, particularly for an arbitrary signal, for a complex signal like this, you just find that it's just multiplication, because we've got e to the I omega t, same differential rules apply for e. It's got this magic quantity that exponent just comes down, and that's all that happens. So we just see that our original signal is multiplied by I omega. So whenever you differentiate by time, you can just multiply by I omega. So differentiation has also been trivially simplified to multiplication. And by reverse, you can also say that integration going the other way is just division by I omega. And these are really, really staggeringly useful. That you want to turn something like acceleration into velocity, or velocity into acceleration. You just multiply or divide by I omega. It's trivially easy, whereas otherwise it would have been really quite difficult. So taking this back to real systems, we have these kind of systems called linear time invariant systems I talked about in lecture 4. And they do things like scale a signal. So if we put in a signal c in e to the omega t, we get something out. This y is, our signal out is g, gain g times x. So if you do that, you can expand that out, and we can just define a new amplitude that c out is g times c in, and we'll get the same form as we put in, just with a different c. What about something else it might do? It might delay the signal, this type of system. So we get x is t minus tau. So we'll put that in. It goes into the exponent because that's where time was. And we can actually just separate that out and do the same sort of thing, that we can just say that we're going to split up the exponential, bundle the e to the minus I omega tau into c, and we get a new value of c, same form again. Differentiation with respect to time, we just saw this. It just comes down as an I omega, bundle that into the c, and you just get another thing in the same form out, just with a different c. And integration, something else that could be difficult. It could be potentially be mathematically difficult. It might represent something like energy being accumulated sort of into acceleration in a mass or something like that, or charge in a capacitor maybe. And this is just going to come down as being c over I omega. There's some constant. We won't talk about the constants. Usually in what you're going to do with these, the constant doesn't matter. But effectively, what happens is we just have a new c, where c was the c that came in divided by I omega, and so all of these different operations just turn into changing the value of c. Yeah, same form in, same form out. So this is the same as with the other time harmonic signals. You can have almost arbitrary combinations of all these things, and that you just get out something else with a different value of c is all you'll do. So you don't even need to think about the I omega t. You just go c in to c out, and that's it. And that leads us into this idea that for any LTI system, linear time invariant system, regardless of what it's doing, you can express its behaviour as a transfer function. And this is something that changes the amplitude and the phase of frequency components. And we've written brackets omega because it might behave a bit differently depending on omega. We saw that things like differentiation and delay depended on omega, how they are written as a complex sort of multiplicative factor. But accepting that for any particular frequency, it's just going to get the output complex amplitude is the input complex amplitude multiplied by the transfer function evaluated at omega. And that is really makes very, very complicated systems trivially easy to deal with. It's quite spectacular. And it holds for sums of complex harmonic systems too. So if you've got complex valued Fourier series, which we'll see in the next talk, which can represent arbitrary signals, each frequency component is simply multiplied by its own HW, so the transfer function evaluated at its own frequency omega. And that's it. So really useful. So I hope that's demystified some things. Quite a lot going on there, so please feel free to watch again or look some bits up if you need to. But I hope I've given some practical and sort of more graphical ways of thinking about complex numbers that are more applicable to signals. So to summarise, a complex amplitude C with a real and imaginary part, or amplitude and phase, can capture both the amplitude and phase of a signal in one number. Remember, it sort of has a complex number is like one that has sort of 2 bits. And this Eulers formula gives us 2 really useful things. It gives us a compact notation for time harmonic variation, e to the I omega t. You'll see that everywhere. And it's an easy way to see that magnitudes multiply and phases add. And the resulting signals will work with a complex. The real part describes the real quantity we're observing. The other imaginary dimension is the other quantity we aren't observing that holds the energy when this one doesn't. And often we'll just actually work with these complex amplitudes without ever writing in the e to the I omega t or the real part or anything else. We'll just work with those amplitudes because it's super convenient. And finally, the action of any linear time invariant system can be expressed as multiplication by a complex gain, the transfer function, which would depend on omega, such that the output amplitude C out is found from the input amplitude C in by C out equals H times C in. And that is fantastically useful, and is another really important reason why we use complex numbers and all this time so much. So next time in part 6, we'll incorporate these ideas into Fourier series, creating complex Fourier series. So I hope that's been useful. Thank you.